Welcome to another IoT Central workshop. Please send any questions you might have in the chat. We will follow up with any unanswered questions using the email address you registered with. My name is Shawn Hymel. I'm a senior DevRel engineer for Edge Impulse, and in this workshop, we're going to look at doing image data augmentation and how that can help create a more robust machine learning model. Edge Impulse is the world's leading embedded machine learning platform. It helps you build a full end-to-end machine learning pipeline to accomplish a variety of ML tasks, from regression to vibration and sound classification to object detection and predictive maintenance. You can import data from any sensor and deploy your model to nearly any device. You maintain control of the data and the firmware the whole time. The Edge Impulse Studio is an online platform that handles everything, including data collection from your embedded sensors, labeling the data, performing any pre-processing calculations, and training machine learning models. This end-to-end project is known as an impulse. You can then test your impulse on live data with a connected sensor. After, the studio will guide you through the process of creating firmware or a library that will run your impulse on any number of platforms. This includes your pre-processing code, trained neural network, and any anomaly detection code you may have so that you can perform inference locally without an internet connection. Data augmentation is the use of mathematical or automated transforms on existing data to generate new samples. For example, you can see in this slide where we take an original image of a resistor and then flip the image vertically and horizontally, and that's in that top left box that says flip. This helps us create or train a more robust machine learning model. Otherwise, you might find that your model is looking for things like the shadow or a particular glint or glare that happens to be in all of the images of that particular class. If we flip the image or rotate it or transform it, that shadow is now in a different position. And ideally, we want the model to be able to recognize this object or whatever it might be, regardless of where those slight variances might occur. So we move them about or zoom in or add noise in order to create this robust model. Here are a number of simple transforms. We can rotate the image, we can flip it, we can translate it, which just involves moving the image side to side or up and down. We can crop or zoom, or maybe zoom out if we don't mind some black bars or trying to expand the pixels on the edges. We can also add some noise. With these very simple transforms, you can see that we've created 12 new images from this one original image. We would repeat this for all the samples in that data set. For example, if we started with 250 original images of, say, this resistor, we would now have 3,250 new images thanks to data augmentation. This helps us expand a data set and give us that more robust training set to create a better model. And this is just a simple example. We could combine augmentations like, say, flip and add noise, or flip, rotate, and then add noise. The possibilities are endless, and there are even some that I didn't mention here, such as playing with the white balance or skewing some of the colors. To start this demo, head to github.com/ShawnHymel/computer vision with embedded machine learning, separated by dashes, in order to see all of the example code, projects, and solutions used in the Computer Vision with Embedded Machine Learning Coursera course. The first thing we want to do is head to the datasets folder. Feel free to make your own dataset for this, but I'm going to start with something so that this is easy to do while demonstrating how data augmentation works. I'm going to download the electronic components-png.zip. I'm going to click download and let that download for just a moment. From here, we want to extract this and wait for that to finish. Feel free to go in here and take a look at some of the examples. Background is just a blank background. I believe it's a sheet of paper. We have a capacitor facing front, back, and left and right. We also have a diode, an LED, and a resistor. If you take a look at the properties, you can see that these are 96 by 96 PNG files with a bit depth of 32 bits. They're all in color. We will transform these to grayscale when we go to create our project in Edge Impulse. From here, go back to the front page of that repository and go to 2.3.5 Project Data Augmentation. I don't need to see these downloads anymore. Let's view the solution. So yes, we are going to be looking at the solution to one of the challenges in the course, but it's a good starting point for viewing data augmentation and seeing how it works. There's a button, if you scroll down, that says Open in Colab. Let's click on that. Note that to run this, you will need to have a Google or Gmail account because we're going to be running things in Google Colab, or feel free to download the Jupyter Notebook and run it on your own instance of Jupyter Notebooks. Let's Shift Enter to run these cells. You'll want to run this first cell. It'll likely pop up and say not authored by Google. That's fine. Click Run anyway. On the left-hand side, you can click the little folder icon and you can get a view inside of the, I suppose, the drive for the computer where we can store files. I'm going to upload that zip file because it's going to be easier than trying to upload all of the image files manually. And I'm going to put my mouse between these two cells and create a second code cell, and I'm going to call an unzip command. All I'm going to do is just tell the computer to unzip it. This exclamation point is a command that says don't run a Python command, but run a Linux command line command. And unzip is a tool in the Linux instance of this Colab. And if we refresh the files, you can see a new folder has been created with the images we just saw earlier. From here, you can right-click on that folder and say Copy Path. We want to change our dataset path, this is the input data, to be electronic components PNG. And it's looking for the individual classes inside of there to perform the transformations. Then we're going to run the cells. So Shift Enter, we don't need to change anything else. Shift Enter again. And here are the transform functions. The first flips left and right, up and down, and then up and down and left and right. So it creates 3 new images. That's just defining a function. This is encouraging the students of the course to create their own functions here. The next one, we're going to provide a number of rotations, and this is given by an array. If we scroll down to where these functions are actually called, you can see we rotate them 45, 90, and 135 degrees. We are not combining any of the transformations right now, but rather just doing them individually. The next is create random zooms. This is where it zooms in and then crops the image, so it gives the impression of we're closer or farther away from the subject or the electronic components. So we'll Shift Enter there. Then we want to create a random set of translated images. This is where we take the image and just move it over a little bit. It's randomized, but up to no more than 1/4 of the width or height away. So they're not completely shoving the subject off of the frame. We want to still keep that body of the component in the frame. So Shift Enter there. And scroll down, finally we add different types of noise to the image. Down here you can see that we add Gaussian and salt and pepper noise. To do these transforms, I'm using a number of different libraries. The first is skimage. This allows us to call things like random noise, to add noise. It's really pretty straightforward to do this. It's changing the pixels based on what these functions are programmed to do. We also have the transform and warp within inside of skimage. We can transform and scale, and we can transform and rotate. So skimage is super useful for providing these transforms. The only thing we didn't do is sktransform for the flipping. We can do that with NumPy. So once we have those, let's scroll down to where it says perform transforms. And this is the actual process of calling the individual functions to perform those transforms. And if you refresh your files, you can see output, which hasn't been done yet. Oh, that's because it's in a function. That's why. So the transforms are not done. It's in a function. When we run this final cell that contains Python code, this is where it reads in each individual image in the input library, performs a number of transforms, and then saves it in the output directory that's been created over here. Once that's done, before we run the final cell, I want to print something for you. Let's take a look at the number of files in our input capacitor class. So we're going to copy this path. We'll paste it here. And let's take a look at the capacitor one for the output case. We'll refresh. Yes, background, all the classes are there. So capacitor, copy path. And we're going to list out the contents in each of these directories. And we're going to print the length of that vector. So you can see the original capacitor folder contains 50 images. After our transformations, that now contains 800 images. So we've added quite a good number of images, and we could do even more if you modify some of this. You could easily create thousands of images based on those original images, and we're going to go ahead and zip those up. This might take just a moment. Refresh, we see that augmented dataset.zip, and we want to download. Once you get the pop-up, click Save, and we will want to go into our Downloads folder and then unzip this. Unfortunately, Edge Impulse does not have a way right now to take in a .zip folder, so we're going to have to upload the images manually, but we can do them in groups at a time. Feel free to go into the augmented dataset, take a look in here, and you can see all the new images that have been created. With that done, head to edgeimpulse.com and create an account if you have not done so already. I'm going to click Login. I'm going to create a new project. I'm going to call this Electronic Components Augmented. Click Create. You'll be presented with your new project. We don't need this pop-up. Let's go to Data Acquisition. Let's upload new data. We'll choose Files, go into our Augmented Data Set, go to Background, Control A or Command A to select all the files, click Open. Yes to let it automatically split between training and testing. We're going to enter a label. This is going to be our background, and we're going to begin the upload. For this data augmentation, if you see some items that failed to upload, there's a good chance that because of the randomness of some of the transforms, they look exactly the same as some of the other photos, so you can just ignore them for now. Let's repeat this process for capacitor. We're going to do the same thing again for the diode. Then let's go to the LED. When that's done, finally we will do the resistor. When you have all of your files uploaded, I recommend going back to data acquisition and making sure that you have a fairly balanced data set with about equal number of samples per class, as well as about 80% in your training and 20% in your test data. Go to test data, verify you have a balanced set again, and we are good to go. Let's create our impulse. These don't need to be very large. In fact, they can be 28 by 28. The studio will convert those, crop them, rescale as necessary to shrink the 96 by 96 images to 28 by 28. You will find that for this really simple example, this resolution is just fine. Let's add an image processing block. We'll add a learning block. We're not going to do transfer learning. We're going to do basic keras. So let's add there, save impulse. Go to image. We don't need color images. We're not trying to read resistor bands or anything like that. We just want grayscale. So let's save those parameters and we'll click Generate Features. This will take all of those images, scale them to 28 by 28, convert them to grayscale, and save those numerical outputs for us. That way it's a little easier when we go to the neural network classifier to train everything. It will just save us some time in the future. When that's done, feel free to take a look at the Feature Explorer to see if you have groupings of classes. The more they are grouped together and separated from one another, or the more the groups are separated from one another, the easier your model will be able to train. With that, let's head to the neural network classifier. Let's try a few more cycles. 3216 filters for a two-dimensional convolutional layer. Looks good. With that, let's click Start Training. Once the model is done training, feel free to look at the accuracy as well as the confusion matrix to see how well the validation set performed. To really test it, let's go to Model Testing. We're going to click Classify All and wait another moment while the model classifies all these test samples. Once your test is done, scroll down to take a look at your model results. You can look at the confusion matrix to see if there are any false positives or false negatives and which images end up kind of looking like other images. Note here that we have about a 97% accuracy on our test set, which is pretty good considering that we started with a fairly low number of image samples per class. I have created a public version of this project at studio.edgeimpulse.com/public/36800/latest. If you would like to take a look at this project, play around with it, you can also clone it in order to make changes. Additionally, I also have a non-augmented version of this at studio.edgeimpulse.com/public/36514/latest. If we go to model testing in the non-augmented version, you can see that the accuracy is significantly worse with a number of false positives and false negatives among the classes. I hope this helps demonstrate how and why data augmentation can be used to create a more robust and usable model without needing to take additional images. That being said, note that getting original images is the best way to go, but from there, data augmentation can help you. If you're interested in learning more about classifying images and object detection, check out the Edge Impulse Computer Vision with Embedded Machine Learning course on Coursera. We cover convolutional neural networks, how to train them with images, and then how to deploy them on embedded systems. I want to thank IoT Central for hosting this workshop. You can find more workshops and Edge Impulse microsessions at iotcentral.io, where this video will also be available on demand starting tomorrow. If you have any questions about Edge Impulse or you'd like to show us something you've built with Edge Machine Learning, please create a post at forum.edgeimpulse.com.